Hello everyone. Today, this example that we're going to do is going to look at Mr. Potato Head bungee jumping using zigzag. We are going to continue our talk of the conservation of energy, but we are going to add a new term into our equation. Tonight is going to be all about a new kind of energy called elastic potential energy. So by the end of this video, you are going to be able to add a new term into our conservation of energy equation that describes elastic potential energy. So just a brief review, remember that our conservation of energy equation looks something like this. E initial plus the work done by external forces is equal to the total final energy. So the total initial energy plus the work done by outside forces is equal to the total final energy. So remember from yesterday we expanded this term and this term into potential and kinetic energy, but this time we're going to add another term dealing with elastic potential energy. So that's going to look like our U, I'm going to call this G, U sub G for gravitational potential energy initial, plus, remember we had kinetic energy initial, plus, now this is where we're going to add our new term. We're also going to call it U because it's a form of potential energy, but it's elastic potential energy. So I denoted that with a little E. Okay, and that's going to be initial. And we have the work done, so we have plus the work done by our external forces. And that's just going to equal our gravitational potential energy final, plus our kinetic energy final, plus this new elastic potential energy final. So here we have this long equation to describe situations where we're using elastic potential energy. But first we should probably talk about what is elastic potential energy and how do we describe it in physics. Well, basically elastic potential energy all comes down to something that stretches, like a spring or a rubber band. So energy stored in a spring. And of course we can model a spring with a rubber band. So the first thing that we need to look at here is something called Hooke's law. And Hooke's law goes something like this. If you have a rubber band or a spring or whatever it may be, and you are stretching it and looking at the force required to stretch it, you can describe a spring by the following equation. Force is equal to K, which K is called the spring constant. It's kind of like the coefficient of friction, in that it's going to describe the properties of the spring or the rubber band. Not every spring is going to be exactly like this rubber band. There are springs in car suspension systems that need to be a lot more stiff than this, and there are springs in your pen or pencil that should probably be a little less stiff than that. So that K value just describes what that is. And then the rest of Hooke's law goes, it's the force required is the spring constant times how far you stretch it. So if we look at two different scenarios of me stretching the rubber band, first I'm going to stretch the rubber band this far. Okay, that requires some sort of force. And now I'm going to stretch it this far, and that requires a greater force because I'm increasing the distance that I stretched it. Hooke's law also gives us a very useful graph as well. So if we have a rubber band and we're stretching it, let's say we would like to plot the force required to stretch it versus the distance that we stretch it, what kind of curve are we going to get here? So remember from Hooke's law, it says that the force is equal to the spring constant, which is just some number, times how far you stretch or compress that spring. So in this case, I'm going to pin it here, and I'm going to stretch it. And as I stretch it, as the distance increases, the force required to stretch it also increases. And it turns out that according to Hooke's law, this is in a linear fashion. Okay? And if you think about y is equal to mx, the equation that describes a straight line, you can relate it to Hooke's law, just like force is equal to kx. So we have our slope here, remember m and k, we have a slope here, and that slope is going to be equal to k, or the spring constant. So that slope can be really, really high, meaning that it would be really, really hard to pull this apart, or it could be really, really low, meaning that it's really easy to pull it apart. Okay, so we've already talked about forces, but now the question is, how do we turn that into energy? After all, we are talking about energy. Well, if you remember from yesterday, our equation for work was force times distance. Well, hey, you know what? When we stretch a spring or a rubber band, we're applying a force over a certain distance. We're putting energy into this system. So, well, that's great. We have a force and a distance, but look at this. We also have a force and a distance here. Well, what happens if you multiply force and distance, especially on a graph like this? Well, you are going to get the area underneath the curve. If you multiply force times the distance, you are going to get the area underneath the curve. And it turns out that this area right here is going to equal the work done. Let's find an equation for this area underneath the curve. Remember that we know the area of a triangle is equal to 1/2 base times height. And we just said that the area underneath the triangle is going to be equal to the work. So we can substitute this in. Work is equal to 1/2. The base here is going to be our distance, or x, and our height here, this is x right here, and our height is going to be the force. Okay, but remember from Hooke's law we said that force is equal to k times x. So what we can do is we can substitute this force in for kx, and we're going to get W for work is equal to 1/2 x times kx. So all we did is we took this and we plugged it in here. So now what we can do is we can simplify this equation a little bit, and we get work is equal to 1/2 kx squared. So remember that when I do work on an object, I'm giving that system energy. I'm doing work on the system. So that means that this is in fact our equation for the elastic potential energy. That's 1/2 kx squared. So now let's work a problem using elastic potential energy. So the very first movie that I saw when I was a little kid was Toy Story. And there's a particular part in one of the movies where Zigzag is allowing all of his friends to bungee jump using his body. So today, this example that we're going to do is going to look at Mr. Potato Head bungee jumping using Zigzag. So first, let's set up our situation here. There's Mr. Potato Head. And remember that our first step here was to define our system. So the system that we're going to look at is Mr. Potato Head and the Earth system. So I'm going to draw a dotted line around my system. Remember that was step 1, was to define our system. Our step 2 was to define our initial and final conditions. So our initial condition up here is that Mr. Potato Head is going to be jumping from rest from the roof, and then he will be fall down, and as he falls down, he will land safely thanks to the potential energy stored in the stretch of Zigzag's spring. What is the spring constant of Zigzag? We defined our system, we defined our initial and final conditions. Now we're going to write our conservation of energy equation and set up some bar charts. So let's write the very general form first. We're going to get E final plus the work done by external forces is equal to E final. Whoops, this should be initial over here, initial. And now let's plug in our new terms that we have. Remember, we have a potential gravitational initial. We have our kinetic energy initial. We now have our elastic energy initial. We have work done by outside forces, and that's going to equal gravitational potential energy final. We have our kinetic energy final, and we have our elastic potential energy final at the end there. So let's draw our bar charts here to see if we can track the energy through the system. Initially, Mr. Potato Head has some sort of gravitational potential energy above the ground. So we're going to give him 1, 2, 3, 4, 5 units of gravitational potential energy. We said he's jumping from rest, so this is going to be going to 0. We said that at the very top, Zigzag's spring isn't going to be stretched out at all. The stretch is 0. That means that the energy stored must also be 0. Okay? Now, Mr. Potato Head isn't wearing a jetpack or anything like that, so the work done by outside forces is also 0. And now we can look at the final side. So at the very bottom, his final gravitational potential energy is 0 because he's at the very bottom. So that one's going to be 0. If he lands safely on the ground, then that one should also be 0. And all that's left is the potential energy stored in Zigzag's spring. And because there's no other energies on this initial side, or work that's being added to the system, it looks like that it has to equal 1, 2, 3, 4, 5 units of energy. So we can rewrite our equation now. And it's going to go U, G, our potential gravitational energy, is going to be equal to our final, this is initial, this is our final elastic potential energy. So now we can plug in our equations here. We have M, we have G, we have H, and that is equal to our 1/2 kx squared. Now if we assume that Zigzag's spring is stretching the entire height of the house, then that means that x is equal to h. And we can rewrite this as mgh is equal to 1/2 kh squared. And looks like we have some sort of cancellation here. So we're going to get mg is equal to 1/2 kh. And remember, we're solving for k. So let's rearrange this equation. And we're going to get a spring constant of 2mg over h. So this is going to be the mass of Mr. Potato Head, the gravity, and the height of the house.